I'm a computer scientist at Math and Computer Science Division and Leadership Computing Facility. And today I'm going to talk about scientific domain-informed machine learning. This could mean wide range of topics. I'm going to focus on a couple of case studies that we did where we sort of systematically incorporated the domain knowledge into scientific applications. And this is a joint work with Preeti, who used to be at ALCF, Venkat, Kumar, Vitali. So this is one case study, another case study with Jiali Wang and Rao Kotamarthi from AVS at Argonne. Okay, so broadly speaking, the DOE scientific data for machine learning can be sort of grouped into two major classes. One, regular domain where we have spatial data, there is a lot of images. Images are, you have a lot of spatial correlation in images, and all the convolutional neural nets with the deep learning and so on and so forth, they exploit this particular property, the spatial correlation in images, and they build features, or hierarchically build features, and then extract information from those features. Either you can use that for classification or further analysis. And then temporal is, again, if you can look at the wind data, the weather data, and so on and so forth, they sort of come from an underlying process that has a temporal correlation, right? So there is some sort of a sequence that repeats over time. They have a periodicity, and then you can sort of exploit using statistical or advanced statistical and machine learning methods, which are exclusively developed for exploiting the temporal correlations. On the other hand, irregular domain, where we are going to sort of see some case studies today, can be again further subdivided into tabular data, where you have just collection of data, a set of rows. Think of this as a sort of your CSV file or Excel file. It doesn't necessarily come from some spatial or temporal domain, and it can be just data collected over some sensors or some observations, some experiments, and so on and so forth. Another one being graphs, where you have edges and vertices, and you are sort of using the graphs to model the underlying physical process, and the data generated are sort of coming from these graphs. And we cannot directly apply convolution on graphs because they don't have spatial correlation, or even the temporal methods where you don't have this underlying structure, the temporal correlation or the spatial correlation on graphs. So you have to explicitly use methods that can deal with graphs. Manifolds is another. Manifolds and point clouds, you can think of this as points that sort of observations that lie in some sort of that comes from a larger dimension, but they sort of lie in a different manifold. Similarly, point clouds. So these type of data need some sort of special treatment. We cannot just take this data and plug it into the out-of-the-box machine learning methods and expect to perform as good as they perform on images or on time series data. All right. Okay. So this talk we'll be focusing on irregular domain and looking at a couple of case studies. So what are the challenges in the irregular domain? So at the center, we want to apply machine learning methods, but first and foremost, we need machine learning methods that explicitly take into account the irregular domain, right? So the irregular domain, it's not any irregular domain, but irregular domain, scientific domain, and we know a lot about those domains, right? So either from first principle models or the simulations or the underlying processing from which this data is collected, we know a lot about the domain. So how to incorporate this domain knowledge into machine learning methods that is customized for irregular domains. Okay? And then the third thing is automation, where the machine learning pipeline is complex. Starting from pre-processing to feature engineering to model selection and hyperparameter optimization. So you have a lot of choices, and especially when you are going from the regular domain to irregular domain, whatever the parameter values, good parameter values that or good sort of a machine learning pipeline that or the feature engineering that may not be generalizable to irregular domains. So again, you have to start from scratch. So we need a good automation. Otherwise, we will be spending a lot of time in figuring out what is the right method, what is the right set of parameters, and what is the right pipeline for developing machine learning methods for irregular domains. And finally, scalability. So how to scale these machine learning methods on our systems, on our big systems. Because for images, I have heard several talks on scaling deep learning methods for images. So the underlying principle is that there is dense matrix multiplication, and you can do good performance scaling on a single node level, and then you can exploit the algorithmic characteristics for this image-based deep learning for bigger machines. But when you move to irregular domains, at the node level, for example, take graphs. You have to deal with sparse matrix multiplication rather than dense matrix multiplication. So the type of workload completely changes. And this also sort of changes how the communication is going to happen between the nodes. So the scalability challenges are going to be completely different for the irregular domains, and we need to sort of come up with new methods to scale this on big machines. So this talk, I'm going to focus on one of these challenges, and Prasanna took the two case studies that I mentioned. We will sort of talk about how we incorporated domain knowledge to improve the performance of machine learning methods. So the two case studies, the first one is scientific application performance modeling. Since we are in the facility, one of the key question that we always try to address is, given this application, can we predict the performance under different conditions, so different input sizes, different node configurations, and so on and so forth. And the second case study is surrogate modeling in weather simulation. Okay, so predictive models, I don't need to justify the need for the predictive models, starting from Hank Hoffman's world-changing ideas to Sam Williams' roofline model. Predictive models, predictive performance models play a central role in many different HPC settings. But coming up with analytical performance models is still a challenging task. The hardware is getting complex, and it's getting a lot more complex, and finding analytical models that can help us to sort of predict the performance is getting even more challenging. Machine learning performance modeling can bridge this gap, and moreover, these models can help us to sort of understand or find knobs that impacts the performance, and we can use those models for, let's say, for doing ensemble jobs with balsam workflows, or use those models to do performance tuning, or find the right set of configurations that will make this application run well on the particular target architecture. So what is the challenge facing machine learning methods? So it's not the data that is coming from simulation, they are not images, especially the performance data, right? So they set up inputs, and we run this application on big machines, and we look at the performance. What type of machine learning method we need to use? And then if we look at the different types of supervised learning methods, right? So there is this thing called no free lunch, which means that no single supervised learning algorithm is going to work well on all data sets. So it's up to us to find what is the right algorithm for the given data set. And given this data set is unique in many respects, we have to sort of understand what type of method works well for the performance data. So the central aspect in many supervised learning algorithms is the bias variance trade-off. So this is the reason why there are several different learning algorithms. Okay. So if you see this bias variance trade-off space, so something it looks like this. So take one single supervised learning method, and that method has sort of a limited functionality or limited capacity to explore different types of functions that can model an input to the output. Okay, so that function, so the best function that this particular algorithm can find is this f star. Okay. And you start from this f hat, to begin with, and then you use the training data to reach to f star. So that is the best function that you can model with this training data. And the distance between this function and the best possible function in the set of all function space is called bias. So this is the approximation error. And the step that you have to take from this f hat to the f star, because you need training data to move from here to here. If you don't have training data, you cannot even reach the best possible function that particular method can reach. So you need good amount of data to reach the best possible function this particular method can reach, and that distance is variance. And the distance between that best function that a particular method can reach and the best possible function f that can model the given data is called bias. And different supervised learning methods have different sort of bias and variance, and so using training data, using right hyperparameter settings, you try to reduce the bias and variance. If you reduce the bias and variance, you will have highly accurate and highly precise results, and this is the region that you want to be in. Whereas if you have a high bias and high variance, you are all over. Okay, and then there is another couple of settings where you have a high bias setting and high variance setting. Again, you need to be reducing both of those things. Okay. Again, if you are taking supervised learning methods, so then if you look at classical methods, there are different subgroups of methods: regularization, instance-based, recursive partitioning, all the way up to bagging and boosting. And then if you take the deep learning methods, you have several different varieties or several different types of deep learning methods. So which one is better suited for performance modeling? Okay. So another thing to look at is, if you take classical methods, if you choose one method in one particular class, let's say bagging, random forest, you can choose that particular method, and then you have to set the hyperparameters. Whereas if you go for deep neural nets, it's up to you to find out what is the right architecture. So the deep neural net that we used, first we looked at the multi-layer perceptron, where we have inputs and multiple hidden layers, and which are connected to the output. The output is the performance. Okay, and the network architecture is shown here. So basically, you start from this input layer. It takes so 10 inputs based on the application. These inputs can differ, followed by a dense layer of 512 units, followed by dropout to avoid overfitting. This is sort of a regularization mechanism. Remember the bias. So by using dropouts, you can sort of reduce overfitting and try to improve the performance. And you basically repeat this a number of times, and then finally you have the output layer. So this is the structure of the deep neural net that we used in this study. And we looked at different applications and platforms. And we didn't go and do new set of experiments. So these are the experiments that were done in the past, and we reused that data for our study. So the machines include Mira, Vesta, Edison, and Hopper. Edison and Hopper at NERSC, and Mira and Vesta here at Argonne. And the mini apps that goes from mini-MD, mini-AMR, mini-FE, and LAMPS. And the number of training points is given in this bracket. So basically, it ranges from 2K, 1K. So mini-FE, we had a lot more points, up to 15K. LAMPS, around 1K points. So, and the experiments were run under different input sizes. And the experiments go up to 1024, 496, 8192, and 1024 nodes for different applications. Okay, so the idea is to use fraction of this input, a fraction of this data, and predict the remaining data and see how well we can do in terms of prediction accuracy. Okay, so the first thing we looked at is the impact of feature engineering. So this is all about incorporating the domain knowledge. Okay, we considered several supervised learning methods. Our baseline is a linear model, linear regression, and then goes for ridge regression, k-nearest neighbor, decision trees, support vector machines, Gaussian process regression, extra trees, random forest, gradient boosting regression, extreme gradient boosting regression, and deep neural net. Okay, so we considered sort of one method from each of these classical method class and one deep learning method. And then we used this data set and then incorporated the feature engineering. So the first one, no feature engineering, we directly use the application input parameters without anything, and then we want to predict the application performance. Okay. The second set is the future engineering set. In addition to the application input parameters, we included several features. Okay, so these features are basically coming from domain experts, and so I listed some of them. The first one being the ratio of application problem size and the number of processes. Okay, and the second was the inverse of the number of processes to capture the scalability. And the third one is binary logarithm of the number of processes to sort of capture the communication. Okay, so the idea is it's not the model that we are going to build is not only just function of input and output, but we also want to help or incorporate the domain knowledge by using these features, something that captures the communication, something that captures the scalability, and something that captures the amount of work done at each node. Okay, so these are the future or engineered features. Okay, and in this plot, what you see here, okay, is this. So the one with the slanting line is no future engineering, and the one with the cross is future engineering. Okay, just look at the performance of the linear model. Without future engineering, so on the y-axis you see R squared. R squared is a way to see how well your model explains the data or how well your model fits the data. 1 is the best score that you can get. So what you see here is without future engineering, linear model has a terrible performance, which has a median R squared of 0.55. And this box plot basically shows the distribution of R squared values computed over 2080 cross-validation. Okay? So the reason why the typical way to do cross-validation is 80-20, but we reversed to 2080 because we want to do this modeling with a constrained data setting. So let's say we have 20% of the data and we want to predict on 80% of the remaining data. Okay, so and then this is repeated 10 times and you get this box plot. And what you see here is without feature engineering, linear model is terrible. Okay, but then with the feature engineering, the performance, the R squared, the prediction accuracy shoots up. It's almost close to 1. It's between 1 and 0.95, right? Similarly, you can see that trend in almost all the methods: ridge regression, k nearest neighbor, decision tree. So these are all more sophisticated methods which can model the nonlinearity in the data without the need for future engineering. So if you even look at the deep learning, without future engineering, on a median R squared value, you can get 0.9899. But with feature engineering, you sort of reduce the worst case behavior or worst case performances. So what is striking is a linear model with feature engineering is almost as good as deep learning with feature engineering. Okay, so this is what incorporating the domain knowledge is going to give you, because by incorporating or using those type of features, basically allow us to increase the prediction performance as good as deep learning models. Okay. So the second thing is we did this and compared. So the training was done on different GPUs. These are more or less modern GPUs. K40, this is on our Cooley single node, and then we compared the performance of the training on P100 and B100 NVIDIA machines. What you see is a normalized training time and normalized inference time. Normalized here is basically we compute the total training time and divide that by number of training points. And the inference is the same. Compute the total inference time and we divide that by number of inference points. So what you see here is this. So in all these different platforms, so the classical methods does not leverage the GPUs, and the deep learning method leverage GPUs. Okay. So this runs only on the host. And what you see here is different GPUs does not results in significant time differences. What matters is the algorithmic complexity. Even with the use of GPU, the deep learning method, the deep neural net are much more computationally expensive than all other classical machine learning methods. Okay, so Impact of training data. So we started with 20% training data. So far, the results that you have seen are 20% training data. And then we started reducing and sort of increasing the training data to see what is the impact of the training data on the prediction accuracy. Again, y-axis you see R squared, and these are all the box plots, and you see the linear model without feature engineering, even if you throw in more data, it is not going to improve because there's not a nonlinearity in the data. Okay? Whereas these methods, let's say random forest, gradient boosting, extreme boosting methods, and deep learning, they already have a capacity to sort of capability to learn the nonlinearity. So that's why their performances are higher. And in fact, these methods sort of leverage the increase in the training data and increases the accuracy. So here we do see that nonlinear methods leverage larger training data and increases the accuracy. Okay. So the next thing that we did is transfer learning, right? So you run one application on one platform, and then you want to run the same application on another platform. And here the question that we asked is, can we use this transfer learning to sort of increase the prediction accuracy and reduce the amount of training data that you need when you move from one platform to another platform? Okay. So here you see the deep neural net architecture on one platform that we used. We trained it on this 20% training data. And then when we move to the platform 2, what we do is we sort of freeze all the weights of the top layers. So here we have 3 layers, right? So layer 1, layer 2, up to layer 2, we freeze the weights, which are basically coming from this network. And then retrain. We take 1% of the training data from platform 2 and retrain only these. So the idea here is the underlying process or the underlying phenomena that generates the data, which is the code, remains the same, but there will be differences between different platforms, and we can capture that by just readjusting the weights at the top layers without retraining everything. Because to retrain all of them, we need more data, right? So if we just need 1% of the data, then it is enough to sort of retrain only the last layers. Okay. So these are the results of the transfer learning. Okay. So what you see here, in all these cases, transfer learning helps. Okay. So here, this is the no transfer learning is one in which you don't use the 20% data train and then move the model. You directly take 1% data and try to learn. Whereas in the transfer learning case, you learn from platform 1 using 20% data, and then use 1% data on the second platform to retrain, and then look at the remaining 99% data. So what you see here is overall transfer learning helps. So significantly, even in statistical sense, for all these 4 applications. So here, MiniFE Mira means you are learning from MiniFE Edison, and then you move and evaluate on MiniFE Mira. MiniFE Edison means you are learning from MiniFE Mira, 20%, and then you move to MiniFE Edison. Similarly, MiniMD Vesta and MiniMD Hopper. Remember that these are 2 different machines in 2 different places with different architectures, and transfer learning here significantly helps to improve the accuracy, especially when you are dealing with limited data. Here is another important study. So here we looked at, okay, can we learn from smaller problem size and extrapolate the performance for the larger problem size? Because larger problem size and larger process count, you need to wait in the queue to run the code, to know the performance, and so on and so forth. So is it possible to sort of learn from smaller node count, a smaller problem size, and try to extrapolate the performance for the larger node count and larger problem size? Okay, so overall the performance is terrible. So we know the machine learning methods are very good in interpolation. When it comes for extrapolation, which is sort of outside your training regime, then it has its own limitations. However, what is important here is to see one with the feature engineering, the linear model. So if you don't see the red plot, no feature engineering, the red bar means the performance is so terrible, it's less than 0, so it didn't show up. But what you see here is with feature engineering, you can still do extrapolation. So incorporating the domain knowledge actually helps you to do extrapolation. It's not magic, right? So you incorporated the domain knowledge, so the extrapolation results are going to be better compared to the other one, right? So that's why you see for the linear model and ridge regression with feature engineering, you have at least 0.4, 0.5 R squared when you do extrapolation. We can also see the same sort of thing here, except for the DNN. For some reason, it cannot perform well. But for the ETR, extra-tree regressor to extreme gradient boosting, we see significant improvement in the accuracy using feature engineering. SVM and GP, for both the cases, it didn't work well because it has its own assumptions that sort of the idea of neighborhood and proximity. Both are kernel-based methods, and one possible way to overcome this is to use a different kernel. We use radial basis function, which basically weighted sum of my nearest neighbors. But then when I want to do extrapolation, I don't have any neighbors to do extrapolation, right? So that's why the performance is really bad. Okay, so am I doing well on time? Probably. So the second case study is surrogate modeling weather simulation. Okay. In particular, we were looking at the planetary boundary layer simulation. So planetary boundary layer. So this is sort of at the lowest part of the atmosphere. So here is the free atmosphere, and then so this is the planetary boundary layer. And then the interesting thing is this part of the atmosphere or the planetary boundary layer it changes over time. So at the noon it looks like more uniform, but during the sunset you have sort of different compositions, and the point is it's over time the same place can change in its properties. So basically this is determined by the ground properties, starting from how much sunlight it can absorb and how much it can radiate, and so that is it's the surface radiative forcing determines the nature of the planetary boundary layers properties. So the properties here means flow velocity, temperature, moisture. So those things within this layer are basically determined by the conditions of the ground, or the what happens in the ground. So in weather research and forecasting model, WRF, this is one of the computationally expensive part to simulate. You have to use differential equations, and it's a more physics-based method to sort of estimate what are the flow velocity, temperature, and moisture. So what we want to do here in the simulation, what they do is they do a sort of a grid, and given this condition at time t, the ground properties, they want to predict at the layer. So let's say level 1, what is surface properties, fluxes, and ground temperature given as an input. They want to predict what are the profiles of the wind, temperature, and moisture. And then so this level, this is level 1, and level 2 they want to do the same. Level 3 they would want to do the same. Level 4 they want to do the same, and it goes up to 16 levels. Okay, for the planetary boundary conditions. So from the physical knowledge or physical domain perspective, whatever happens here sort of influences what happens here, and what happens here depends on what happens here and the input conditions eventually, right? So this is the domain knowledge that the domain scientists know, and they use this to sort of develop first principle models, and they use that for the simulation. But our goal was to then can we develop a neural net that sort of mimics closely what the physics is all about? And what you see here is a neural network architecture that we developed. So basically, so the input layer here takes surface properties, fluxes, and ground temperature, and then it is connected to an MLP, multi-layer perceptron, with certain dense layers. And then what you have is the output, which is the profiles of the wind, temperature, and moisture. So this one thing corresponds to this one, okay? And then we connect the output of that MLP, and then connect the input in this fashion to give input to this level. So that is this MLP, Okay? Then we take the output of this MLP, that is this layer, and connect it to the input layer, and then do another MLP and do the prediction for the output. So basically, for each level, we will have the output, and for each level, we will have the input basically connected to each one of them. Okay? So the output of the previous layer is connected. So output of the current layer is connected to the next layer, along with the input. So that's the architecture, and basically this continues up to 17 levels. So the problem is, if you try to build like 17-layer network directly without taking into account any of this physical phenomena, then you will have a high probability of overfitting the data, which we'll see. So with that architecture, so this is what we see as a prediction result. So one thing to note here is, although the problem is a time-dependent problem, a spatiotemporal problem, right? We want to predict how much so what is the prediction accuracy that we can get ignoring the time dependencies? So given this input, can we predict what happens as output, independent of what happened at the time t-1? Okay? The reason for that is then we don't need to keep track of all the things that happened in the past, because that corresponds to storing the data, increasing the memory capacity, and so on and so forth. Okay, so what you see here is the prediction results with the architecture, that neural network architecture that I showed. Level 1, which is close to the surface, we can do pretty good on all the 5 different outputs that we want to predict. But if you start moving up, 2-kilometer range is the top layer, the level 16. The prediction results slowly start getting worse. So this is the output of 2 layers. Okay, so these are the results of 2 outputs. Meridional wind. This is the south-north wind, and up and down motions. On the x-axis, you see the levels. So basically, the horizontal stack that you see, that becomes the x-axis. So 16. So it goes from 1 to 16. And what you see here is a different variance of that architecture. And what is important to note is what is the performance of the multi-layer perceptron that you don't take into account any of the physical domain or physical process. Okay, so multi-layer perceptron, you just build a big network, give this input, and try to predict 85 outputs. That is 16 times 5. Okay, and what you see here is these are the sort of the accuracy. This is a correlation coefficient. So one way to sort of combine all the results. 1 is the best that you could get. So if you're close to the surface, then you have a pretty good correlation coefficient, but then it slowly decreases when you go up. So this has a physical meaning. The reason being that the more you go up, your output depends on the previous time steps. Okay, so that's the reason why this sort of the accuracy slowly start decreasing. Whereas if you look at the MLP, clearly there is a overfitting that is happening here. The performance of MLP is terrible. The rho value, the Pearson correlation coefficient, is between 0.4 and 0.5. Okay. So similarly with the up and down motions, we could see this. Starting from this lower levels, we have pretty good correlation coefficient, but then going to the other levels, it slowly starts decreasing. And again, here MLP is doing really bad. So the previous results are for, we use the training years from 1985 to 1994 and then try to predict what happened the next 1 year. So these are the results for just using only 1 year. Even with only 1 year, so we have one variant, HPC stage. Basically, the idea HPC staged is so previously connected, but then the way that we train is we build the model and then immediately train, freeze the weights, and then build the next level, train, freeze the weights, and so on and so forth. So that sort of results in this weird outlier. But overall, even with 1 year, we can sort of predict the south-north wind very well. The reason being that so we are ignoring the temporal correlations, and then we want to see, given this input, can we predict the output? So that's the reason why we don't need 10 years of data to do this. We just need 1 year of data to capture this correlation. Again, MLP is not doing very well. Similarly, with up and down motions, we could see a similar trend like the last one. Okay, so with that, I sort of come to the conclusion. So we have a lot of challenges when we deal with irregular domains, and the number of ADSP applications and the data science proposals that we started getting, with which we are seeing a lot of these irregular domains going forward, and we are working on several interesting projects. So I just covered a couple of them. There are a lot of work both from the scalability perspective, but also from incorporating the domain knowledge and doing automation with hyperparameter search and so on and so forth. So Elise talked about that yesterday. So a lot of interesting work and a lot of cool things happening here at ALCF. That some acknowledgments: US DOE, NLA, LDRE, ALCF, and Oscar Early Career Research Program. That in my talk, and I'm open for questions.
In a sense, is there like a strategy to it? Like, so you have like, let's say, some basic features, and then you apply some domain knowledge, you get, maybe create some combinations of those original features. Are you adding this to the original set you have? Are you replacing, or is there some like structure to the way you approach it?
No. It's just what you said. So if you have more insights into how to incorporate those features, then one could potentially combine them in a different way. But in the first case study, what we did is, okay, so these are the features that people use in analytical models. Let's use that as features in machine learning models, and I think that was our starting point, and so that made linear model as good as deep learning model.
Just a quick follow-up. And did you do like some kind of sensitivity? Yeah, some sensitivity or some other magnitude comparison of like the value or contribution of a different.
Oh, okay. For this study, we didn't do it. Actually, that's a good point. For a different study previously, we did that, looking at what are the different features that basically contribute to are most sensitive. So we have sort of non-parametric way to estimate the sensitivity of those factors that impact the prediction accuracy. So, yeah, it's possible to do that, but for this study, we didn't do that.